We're on the French-Swiss border near Geneva, and we've come to visit the Large Hadron Collider, one of the biggest physics experiments in the world. Beneath our feet is a 17-mile-long tunnel where scientists have been firing particles at each other close to the speed of light in the hope of answering some of the most fundamental questions in our universe. Things like, what are the basic building blocks that make up our bodies? And why the universe around us is the way it is. For the first time in 4 years since experiments began, scientists have opened up the tunnel where these particles have been fired, and we're going to go down and have a look. Right now, we're down in the bowels of the Large Hadron Collider. Normally this tunnel is closed off and we wouldn't be able to come down here. But because it's been shut down for repairs and some important upgrades, we're able to come down and have a look around. This 17-mile long ring is where particles are accelerated around at 11,000 times a second. They're then smashed together, producing temperatures that are hotter than the heart of our sun. We're 100 meters underground at what's called the CMS experiment. In the center of this machine behind me, the particles that have been whizzing around the tunnel that we saw earlier on are collided head-on, producing a shower of debris. The onion layers of this machine then detect that debris that's thrown off. The scientists have to sift through the information that's produced, about 300 megabytes per second, to try and find some of the rare particles that they've been looking for.
My name is Tejinder Verdi. I was the project leader when we first started taking collision data some years ago. In fact, that was the last time I saw the experiment open. Now what we're doing now is to maintain the experiment, add some bits and pieces which we didn't have time or resources to add, and generally actually improve the experiment in preparation for the next run, where the energy will be increased by a factor of 2. Now, this particular experiment now has discovered a Higgs boson along with the Atlas experiment. Now, we don't quite understand why the mass of this Higgs boson is so low, so we believe there's some other physics. By going to twice the energy, we hope we will find some answers to this question. The protons actually collide head-on. They have high energies, and high energy mean high temperatures, and these high temperatures existed in the early universe a fraction of a nanosecond after the Big Bang. So we now know that the universe contained a Higgs boson. In fact, the universe at that time was much simpler than the universe today, because objects like trees or me or watching didn't exist. So it was a primordial soup of particles and governed by laws of nature at the time. So we're going back in time and looking at a subset of these collisions and trying to produce particles that existed at that time. Now, electrons and photons and neutrinos and the Higgs boson existed, but maybe something else that existed at that time. And what were the other forces? What was the composition of our universe? And then we can probably tell how the universe has evolved a bit more accurately, and how it started perhaps as well.